Greetings and welcome to my new calculus channel. My name is John Gabriel, and in this video I'm going to talk about how we actually got arithmetic operations and why it's important to know how we got them, because at the end of the day they're essential to our understanding of mathematics. So let's begin. Now, for centuries, highly stupid mainstream mathematics academics have had no clue how these operations came to be. At school, you've simply been given rules, you're taught rules, and you memorize them. For example, you're told that when you add certain fractions, you first convert the denominators to the same value, and then you can add them, etc., etc. But you never really understand any of that. You never understand why you multiply the numerators of fractions when you do multiplication in fractions and you multiply the denominators. You don't understand just about everything you're taught with respect to fractions, which is, by the way, how we understand number. So in this presentation, I'll reveal to you how we got these operations, or the arithmetic operators, and how they were transferred from sound mathematics, which is geometry, that has no axioms or postulates, contrary to ignorant mainstream thought, how it was transferred to algebra through the abstract unit. So I'm going to be putting a link to this and to the video once I'm done. So now, the most primitive arithmetic operator is the difference operator. So when we look at two lines, like the red and the blue one, we can tell the difference because we can superimpose the one line on the other, and whatever, or the shorter line on the longer line, and whatever's left over, we know that that must be the difference. Now, how about the addition operator? Well, to realize the addition operator, you have to use the difference or the subtraction operator. You cannot realize addition before you realize subtraction. So, and also, here's another exercise for you to try. Try to define addition without using the difference operator. In other words, without using minus. You can't, because the most primitive operator is the minus operator, okay? And so I've shown you here that you can actually add these two values either like this or like this, but you have to use the minus operator. So you can derive the addition operator from subtraction, but not the other way around. So given two lengths p and q, as we have here, where the difference r, if we want to define p plus q, there would be no way to do this without the subtraction operator. And I'll show you here how you can do it in one of these two ways, but you have to use the subtraction operator, okay? You cannot use the addition operator in the definition of itself. You might have thought ignorantly that you could say p plus q is equal to p plus minus q. That's nonsense, okay, because you're still using the difference operator. So geometrically, one would find the difference of this red line and blue line using similar triangles as follows. So first of all, we take the red line, construct a right angle like this, then place the blue line right at the end. In other words, having it coincide with this point into the red line. Then we connect the end lines of these two lines here, and then we can draw another line parallel to this one, as you see here, and that gives us a difference. So we could actually slide across like this. In my applet here, which I'll also give you a link to, this is basically what it means. So for example, if you had a difference like that, 3, 6, this whole red line is 6, but 6 minus 3 is 3, right? So you start off at 6, put this blue line on top of this red line here like that, and you just move along until you're there, and then you read off the difference. Okay, so in geometry, you don't even care about numbers, right? So this is geometric arithmetic. You're basically dealing with magnitudes, and you can get the exact product or quotient in every single operation. It's not like weak algebra, where you use the abstract unit and you cannot represent everything using the abstract unit. For example, pi and e and square root 2, those are only approximate measures in algebra. Now, of course, you might say, well, what about geometry? Well, geometry has no ideal unit. But if, for example, I said, let this be 1, Now notice that the product of these two lines is always a red line, and then just move this one slightly across like that to get algebraic arithmetic. Then you would see that that this line here times this line here, or the product of two lines, would be the red line. So it would always be exact. So if you could get pi or have pi on this line and 1 on this side, you'd have the exact product. Okay? So now, that's how you would do it geometrically. And as can be seen, the process is fairly straightforward. All you do is produce a line parallel to another line until the difference is established. So in theory, the difference operator is realized even before parallel lines. That is, from requirements 1 and 2 of the elements. These are not axioms as you've been brainwashed to believe. They can be derived systematically from nothing, using your brain, of course. You do need a brain, actually. I mean, if you can't think, well, then all bets are off. So a shortest distance is possible between any 2 points, and any shortest distance can be extended to another shortest distance. And from this same thing here, it's easy to prove that if you wanted to reduce that distance, you can do the same also. Now, when dealing with straight lines in geometry, the difference is therefore trivial. But in algebra, one deals with numbers, okay? So that may or may not have the same abstract unit. So for example, if you had in algebra 1 minus a third, then in geometry, this could be interpreted also as 3 minus 1 equals 2, or anything else. It doesn't really matter, as I've shown you over here with these diagrams. But if you actually look at the algebra, you'll see that in algebra it's represented by numbers and not by lines. And of course, algebra does not have the ability to represent every line or distance, okay? Because there's something called an incommensurable magnitude. No, not an irrational number, because a magnitude is not a number, and a number is not a magnitude. A number is a name given to a measure that describes a magnitude. So the properties of arithmetic on magnitudes in geometry are transferred intact to algebra through the abstract unit, whose size is irrelevant in algebra. And you can watch this video. There's a link here to see how that works. And of course, quotient and products are determined in algebra using the exact same method, but with an extra condition. Okay, what's that extra condition? The similar triangles are subtended on the same arc of the circle. As you see over here, these similar triangles are subtended on this arc or this arc, okay? So these are the similar triangles, and they don't have to be right angles, by the way. They can be any pair of similar triangles in a circle. They have to be in a circle. If they're not in a circle, then the product of this line and this line will not be the red line, okay? Now, it doesn't matter what unit you choose. If you had to, say, for example, do this, and then, of course, let's do this. Make it a 3 here. Or let's rather make it 4. And then this, you think, well, 4 times 2 is not 4. Well, actually, it is in geometry, because 4 times 2 is 8, which divided by the unit 2 is 4. Okay, do you understand that? Right. So it doesn't matter what unit you choose in geometry. You always find the exact result, and you have both the quotient and the product in this scenario here, because 8 divided by 4 is 2, and 8 divided by 4 is 2, right? Okay, so this here is actually 8, and this is 8. Okay, and 8 divided by 8 is 1, and this line here is really 1, because it's really 2 divided by 2. Remember, this black segment here represents a unit. So to make it simpler, you could just do that, and it's easier to see that way, isn't it? Because now if this is 1, then you can say 3 times 2 is 6, and 6 divided by 2 is 3, and 6 divided by 3 is 2. So you've got everything you need here. Multiplication happens to be a reciprocal measure, okay? So it doesn't matter how you decide you want to do it. You can do it either this way or this way, okay? But the answer is the same. And so, for example, if you had pi here, like this, just over 3.14159, whatever, pretty close, then this line here would be the exact value. But geometry doesn't use the abstract unit, okay? So you can watch this video too to see how it works. And finally, I want to show you how to find the product of 2/3 and 6/5. Now, in geometry, multiplication is defined as the reciprocal measure of division. And you can read my article, How We Got Numbers. So this is the definition. A quotient or division is that positive rational number that is measured in terms of two numbers. In its most primitive form, a quotient is simply the ratio of two magnitudes which share a common measure. So you start off the idea of number with a ratio, and then if they both aliquot parts of the ratio have a common divisor or magnitude, because at that particular time there is number, then you can give those lengths names and let it be described by a number. Let the measure be described by that particular number. So if they don't have the same measure, then it's not a number, because that's how we got numbers, and that's what a number means. So you can actually determine this product either this way or this way. And in this 11th slide here, I'll show you how to do it. And over here, all I'm doing is I'm using similar triangles. I'm using book 5 and proposition 12, which is about similar triangles. Why can I do this? Because 2/3 is equal to this. I mean, I can add as many 2's as I like on the top and as many 3's as I like on the bottom, because they're in proportion. And so finally, we know that this result here will be 12/15, because P over Q is equal to P over 1 in ratio to Q over 1, okay? Because the denominator 1 tells us how many equal parts. In this case, there's only one part. How many equal parts are being used in the denominators of these fractions, 12/18 and 15/18. So to get from 12/15 to 4/5, we once again use similar triangles as demonstrated in the previous slides. And as you can see, algebra, which is a weaker form of geometry, inherits all these properties through the abstract unit. The abstract unit doesn't have a size, okay? And the abstract unit in geometry has a size which is irrelevant, okay? In other words, it's used as a measuring stick, but its size is completely irrelevant. Now, so I've shown you all the arithmetic operations, which are derived from geometry, by the way, not from localization of rings in that bullshit subject, abstract algebra, which, by the way, there are some interesting things about abstract algebra. But it's, if you look at how they try to define it, it's all circular, and they're assuming all these facts, by the way, that I've just explained to you. So all these operations of arithmetic are derived directly from geometry. Okay, you don't have them, you cannot understand them unless you understand the geometry. Okay, so I know I've dealt with this in past videos, but hopefully this will be the last one, and everyone on the planet now who watches this will know why you do the operations with fractions the way that you do them, because my brilliant ancient ancestors realized these things before any of you morons did, or any of your ancestors did, okay? And so I'm explaining these things to you so that you understand. This is New Calculus Channel, and I'm John Gabriel. Till next time, goodbye.